Hi, all. So, what I'm going to do today is just go over the recitation group work. This is going to be primarily focused on chapter 1 and 2. And I'm just going to go through it and go over what I think is important for y'all to take away from this. So, this first part, this review, I actually include that because I think y'all need to practice making what I like to call concept notes, which basically you're bringing together, or concept maps, where you're bringing together all the information that you've learned and you're organizing it into a way that makes sense to you and that connects to things you already know. So that's really what meaningful learning is all about, right? If you're actually learning something, you're making meaningful connections to information that you already have in your brain. So for me, I showed you on my TikTok, I think we're going to need to draw structures. And within that, we have like Lewis structures, formal charge, bond line formula, condensed formula. You should be able to go back and forth between these two. You should know all the rules for bond line formula and how to make it. And then I put, you need to be able to do resonance structures, just that kind of thing. I just want you to be able to this isn't all of it, obviously, but I want you to be able to do all of it and just go through everything that you need from this chapter. And all we've done so far from chapter 2 is gone over functional groups and alkanes, anes versus enes versus ines, and some of the background of where those molecules came from. So that's all we've done from chapter 2 is that plus functional groups. So strongly encourage you to do this as a study guide and then use that as you go through your practice problems. So I'm actually going to switch to a different pen. So we're going to draw Lewis structures. Sorry if you can hear my dishwasher in the back. I live in a small apartment with my sweet husband who's doing the dishes. So the first thing here is draw Lewis structures and the bond line structures for each of the following molecules. So again, I talked about how you usually put an atom with a specific electronegativity in the center of a molecule, but you don't really have to do that, luckily, in organic chemistry, because the condensed formula kind of shows you what you need. So that CH3 being first tells me that there's a carbon surrounded by 3 hydrogens, and then the next thing will be a nitrogen. And that nitrogen will have 2 hydrogens on it. But I like to do what they call electron bookkeeping, so we're going to add everything up. So carbon has 4 valence electrons times 1 is 4. Hydrogen has 1 valence electron times 3, 4, 5 is 5. Nitrogen has 5 valence electrons times 1 is 5. So that's 10, 14. So the total there is 14. So then with the lines that we've come up with based on the condensed structure, there's 2, 4, 6, 8, 10, 12. So 14 minus 12 is 2. So then we just have one lone pair, and I'm going to put it around the nitrogen because that's the only one that doesn't have a full octet. The carbon had 4 bonds around it, and hydrogen only needs 2 bonds to get its octet full. It technically follows the duet rule. So the only thing that was short on an octet was the nitrogen. And then if there's no charge on the overall molecule, usually there won't be a charge, like a formal charge that you need to have, but you want to look out for it just in case. But all these look right. Hydrogen has 1 bond, so those are all neutral. Carbon needs 4, and it has 4 things around it, so that's neutral. And then nitrogen has 5 valence electrons, minus 2 electrons on the molecule in the structure, minus 3 lines around it, 3 bonds around it. So the total there is 0. Okay, this next one, CH2, CH2. So when I see that, that immediately sends off red flags in my mind. So CH2, normally you need 3 things around a hydrogen, but I'll just go ahead and draw it like this. This carbon has 2 hydrogens, then it's bonded to another carbon also with 2 hydrogens. And then we'll do our electron bookkeeping. So carbon has 4 times 2 equals 8. And then hydrogen has 1 times 4 equals 4. So that's 12. So we've got 2, 4, 6, 8, 10. 10 electrons used up, so we have 2 electrons left. Now, both of these carbons don't have a full octet. So you could technically put a lone pair on one and do a positive charge on the other, but that's not going to be as stable as a Lewis structure with a double bond there between the 2 carbons. So if we do this one's negative, this one's positive, that's not a very stable structure. This is a much more stable structure, so this is the right answer for the Lewis structure for B. I'll do the bond line formula of all of them in a minute. This is kind of hectic. C is C2H2. That's suspicious, but and it's not in the normal condensed formula. But based on kind of what we've seen the pattern as the carbons being in the middle and hydrogens only being able to bond to one thing, I'm going to start with this structure and then I'm going to do my electron bookkeeping. So carbon has 4 valence electrons times 2 is 8. Hydrogen has 1 times 2 is 2, so 10. So we have 2, 4, 6. So we have 4 electrons we can do whatever we want with. Now, one option is to do a lone pair on each one of these. However, if we did that, now this is technically a neutral carbon because it's 4 valence electrons minus 2 electrons minus 2 bonds, and that's neutral. But it does not have a full octet. It only has 2, 4, 6 electrons. So a better option would be to let each of these carbon atoms share those electrons and make this a carbon-carbon triple bond. So that's C. Wow, I did not make enough room, so I'm going to go on an extra page here. So for A, the Lewis structure we decided looked like this, and so the bond line formula for that is actually just like this. You do have to draw in hydrogens for a heteroatom, but this line right here where it terminates, that's the CH3. The CH2, CH3 for bond line formula would look like this. So that's this structure right here for B. For C, it would just actually look like this. Oh, I drew those hydrogen in, but you don't have to. B could also just look like this. Sometimes with triple bonds, they'll draw the hydrogens in, but it's not necessary in either of these situations to draw those in. Okay, the next one is a little weird. That is D. So we have CH3. So again, we'll just surround our hydrogen with 3, or our carbon with 3. CH2, so 2 hydrogens around our carbon. And then we have CHO. So the way that this is written is a clue. If it was an alcohol, it'd be COH, because the bond would be between the oxygen and the hydrogen. This isn't an alcohol. It's CHO, which is actually, you'll learn as we go through OChem that CHO is shorthand notation for an aldehyde. Just as we go through, you'll recognize that more often. But you know that the carbon is bonded to the hydrogen because the hydrogen comes right after, right? So over and over, we've seen carbon followed by hydrogen means it's bonded to that. But then that oxygen, you can't put it outside of the hydrogen. Like if you were to put it with a bond and a line here, that hydrogen will have too many bonds. So instead, we actually are also going to bond the oxygen to the carbon, very similar to when we had CH3, CH2, CHBr, CH3. We did CH3, CH2, CH2, CH, and we drew the Br as if it was where a hydrogen would normally go, and then we had our CH3, right? So we're kind of following the same principle here where we put the hydrogen and then the whatever's not a hydrogen but's written after the hydrogens in. And then we do our electron bookkeeping. Carbon is 4 times 3, so that's 4 times 3 is 12. Hydrogen is 1 times 1, 2, 3, 4, 5, 6 is 6, and oxygen is 6 times 1 is 6. So that's 12 plus 12, so that's 24. So 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, minus 18. So 24 minus 18 is 6. So we have 6 electrons that we have something to do with. So that's when we look for anything that doesn't have a full Lewis structure or a full octet. So I see 2 things that don't have a full octet. This carbon only has 3 bonds to it, but it wants 4 bonds. And this oxygen only has 1 bond to it, and it wants usually 2 bonds and 2 lone pairs to get a neutral formal charge. So knowing that carbon wants 2 bonds and 2 lone pairs to get a neutral formal charge, I'm going to ask myself, can I make another bond between that carbon and oxygen and then do 2 lone pairs here? That used up 6 electrons, and now everything has a full octet. And it does. And this is a functional group called an aldehyde. And you will learn as we go through organic chemistry that aldehydes are often written with a shorthand notation of CHO. That's not really shorthand notation, I guess. Their condensed formula is CHO. Okay. So this is the condensed formula for D. So the 1, 2, 3. This is what the bond line formula would look like. Some people have asked me, is it okay if you do it upside down, or like either of these ways is correct. So, okay, that's the answer for D. And then E, CH3, carbon with 3 hydrogens around it, carbon with 2 hydrogens around it, and then we know the oxygen is directly bonded to that carbon because it comes after the hydrogens, right? If it wasn't directly bonded, then we'd be confused. And then the hydrogens come after the oxygen. So when it's CHO, the hydrogen's bonded to the carbon. When it's COH, the oxygen is bonded and then the hydrogen. So in this case, it's COH, but there's actually 2 H's. So we'll just draw those on. Okay, so then I'm going to do my electron bookkeeping. Equals 4 times 2 is 8. Hydrogens 1 times 1, 2, 3, 4, 5, 6, 7 is 7. And there's oxygen. 6 times 1 is 6. And then if you have a positive charge, that means you've lost an electron. So actually, we're going to add all these up and then subtract 1. So 8 plus 7 is 15. Plus 6 is 21, but we lost an electron because we're positive, so 20 should be the full number that we have. And now let's count it all up. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so we have 18. So 2 lone pair left to do whatever we want with. And everything I see has a full octet except this oxygen. Oxygen only has 6 things around it, so we can put a lone pair there to fill up its octet. But there's a positive charge on this overall molecule, so we want to do a formal charge assessment to see what has a positive formal charge. Now this carbon starts with 4 valence electrons, it has 4 bonds, it has no lone pairs, so that's 0. Same thing with this carbon here, 4 valence electrons, 4 bonds, so that's 0. And then oxygen has 6 minus 3 bonds minus 2 lone pairs. That equals plus 1. So that's where our positive charge is. And then all these hydrogens have 1 bond to them. So that, of course, makes them neutral because hydrogen starts with 1 minus 1 bond, formal charge of 0. So if I was drawing this out, I would draw CH3, CH2, and then OH2 plus is how I would draw that in condensed formula. Or you could do this. Either one of those is appropriate. Okay, so that's how I approach low structure questions and then also converting it to condensed structure. There's no questions like this, but you should practice going from the bond line structure back to the condensed formula. So if you had this, you should be able to go CH3, CH, CH, CH3, that kind of thing. Oh, my marker bled through on this one. That's okay. I think we can see. So what's the hybridization of the central molecule? This says central molecule of each molecule. Central atom, of each molecule. And what's the shape? So the central atom here is this carbon. So I'm going to look for sigma bonds around it. Here's 1 sigma bond and 2 and 3. This, the double bond is a pi bond. So we have 3 sigma bonds. So we need 3 hybrid orbitals. So that would be 1s and 2 p's combined to make 3 sp2 orbitals. So this is sp2 hybridized. And the shape for that is trigonal planar. Okay, and then right here, we only have 2 sigma bonds. This would be a pi, and this would be a pi. So these pi bonds are made up of overlapping p orbitals, so we need 2 hybrid orbitals to make up the sigma. So 2 hybrid orbitals would be 1s and 1p. So it's sp hybridized, and that shape is linear. And this is just going based off what we talked about in class. We spent a lot of time on that in class. So this is the central molecule here. Oh, and I was doing the carbon, the central carbon there. So this is a central molecule here, this carbon. It has 1, 2, 3, 4 sigma bonds. So it needs 1, 2, 3, 4 hybrid orbitals. So it would be s and 3 p's. So that's sp3 hybridized. Okay, right here we have our central molecule is this carbon. It has 1, 2, 3 sigma bonds right there. So 3 sigma bonds must mean it needs 3 hybrid orbitals. So that would be spp. So sp2 hybridized. So that's trigonal planar. Oh, I didn't do the shape on this last one. sp3 hybridized is tetrahedral. Okay, this one, 4.6. This is the one I talked about that has, this is where formal charge gets hard, is when there's hidden electrons, right? So there's a formal charge here, but you don't see any lone pairs there. That's because the formal charge tells you that the lone pair is there. So what I would do for this is I know that carbon comes with 4 valence electrons, and I can see 3 bonds. So there must be something that gets my total to equal -1. So 4 minus 3 is 1. So we must subtract 2 more to get to -1. So if we have 3 bonds, we need 3 lone pairs or 2 more bonds. I said if we have 3 bonds, we need 2 electrons, not 2 lone pairs. Or 2 more bonds. But bonds are shown. Sorry if you heard my husband talking just then. His video game was loud. He's playing Rocket League. I don't know if you guys play that or not, but that's what he's doing in the background. And his music was loud. Okay. So for this, sorry, I just totally got distracted. You need 2 more things to get to -1 on this here. Valence electron count up, the formal charge calculator. So you could either have 2 electrons or 2 extra bonds, but we would see the 2 extra bonds. So unless they were, I guess, bonds to hydrogen, but if you had bonds to hydrogen, then that carbon would have 1, 2, 3, 4, 5 bonds to it. And that's exceeding the octet rule. So the only way to fill the octet rule and also to get a formal charge of negative is to have this structure. And we didn't really talk about what lone pairs will do, but they will try to go into a hybrid orbital to stabilize and to get as much space as possible around the molecule. So they will go into the sp3 hybrid. So you have your 3 sigma bonds plus a lone pair. So you still need your 4 hybrid orbitals, 1 for each sigma bond and 1 for the lone pair, so sp-p-p, so that's sp3. And then these, there's not really a central atom. They're both the same, actually, so it doesn't matter which one you pick. But there's 1 sigma bond on each side. There's 2 pi bonds over here. This and this is both a pi bond. So if you have 2 sigma bonds, then you need 2 hybrid orbitals. So that's sp. So that's sp hybridized. And that's linear. Okay, so that's question 2. The next question is practicing formal charge. So I think this kind of formal charge is relatively straightforward, and my students typically don't struggle with it. Sorry, the sun is starting to encroach upon my area. Students usually don't struggle with formal charge this way. They struggle more with the formal charge that shows hidden electrons, is what I would say. So I don't expect y'all to have too hard a time with it, but if you are, if it's just not clicking, that's fine. I'm going to spend time going over it just in case, and some people just have different things that are mental blocks for them. Different people's minds work differently, but I think that you won't have too much of a hard time with this. So we're only looking at oxygens. We're looking for oxygens with +1 and oxygens with -1. So you can do one of two things. You can just go through and assign every single formal charge, which is what I would do, or you can get into the habit of knowing in general what makes a neutral oxygen or a +1 or -1. So in general, we know that to be neutral, oxygen wants six things. So whether that's a combination of bonds or lines, or bonds or electrons. And the one we've seen most common is 2 bonds and 2 lone pairs. So you see that in water, and you see that in this functional group. That usually 2 lines and 2 lone pairs usually means the oxygen is neutral. If you see an oxygen with 1 bond and 3 lone pairs, that's usually negative, because 6 valence electrons minus 6 electrons minus 1 bond is -1. I guess I should have done the math on this. 6 valence electrons here minus 4 electrons minus 2 bonds is 0. And then if oxygen has 3 bonds to it, in general, 3 bonds and a lone pair, this is like the hydronium ion that you've seen in Gen Chem. 6 minus 3 for the bonds minus 2 equals +1. So this is positively charged. So you can look for that pattern if you want to, and then you don't have to go through the steps every time. But I am going to go through the steps every time because I think that's beneficial as you first start out. So this oxygen, 6 valence electrons minus, the way I moved my camera, it's now harder to see when my hand's on there. 6 valence electrons minus 2 bonds minus 4 electrons in the oxygen equals 0. So this one doesn't have a formal charge. This is 6 valence electrons minus 1, 2, 3, 4, 5, minus 6 electrons minus 1 bond is -1. So this is negative. Okay, for this one, these oxygens are in the same environment, so we don't have to calculate it out twice. So for both of them, there are 6 valence electrons, 2 bonds, and 4 electrons around the atom. So for both of these, they're neutral. There's no charge on this. So for the first part, 1 has a formal charge of -1. And then we'll see if any other ones do. This oxygen starts with 6 valence electrons minus 3 bonds minus 2 electrons equals 1. So that's +1. So that's positive. So 3 is a +1 formal charge. And then 5, 6 minus 3 bonds minus 2 electrons, that also equals +1. So 5 is also positive. It's a +1. So 5, that's 4, not 5. 4 and 3, sorry, both have +1. And then let's look at 5 to see. 5, this one is 6 minus 2 bonds minus 4 electrons is 0. This is 6 minus 6 electrons minus 1 bond equals -1. And these are in the same environment. Those two are kind of the same. So with that, then we know that there's 2 with a negative charge to this overall molecule. I put -0. -1, -1. So this overall molecule would have a -2 charge. So 1 and 5 is the answer to this question, and 4 and 3 is the answer to this question. Okay. What is the formal charge on the carbon in the following structures? There are no implied hydrogens, so we don't have to worry about implied hydrogens, luckily. We just have to figure out the formal charge. So carbon starts with 4 valence electrons minus 2 bonds minus 2 electrons. So that's neutral. This carbon starts with 4 valence electrons minus 3 bonds, so that is +1. So this carbon is positively charged. And then this has 4 valence electrons minus 3 bonds minus 2 electrons equals -1. So this is negatively charged. So the formal charge on the carbon is no formal charge, a positive formal charge, and a negative formal charge. And this question at the bottom says, in each molecule is the octet full? So we need 8 electrons for the octet to be full. A bond counts for 2 electrons, 2, 2. So this has 6 electrons. So no for A. 2, 4, 6. So no for B. And then 2, 4, 6, 8. So yes for C. And at the very bottom, it says, are formal charge and the octet rule related? So are they related? To some degree, I guess they're related, but for the most part, no. You can have a neutral molecule like A that does not have 8 electrons. A has 6 electrons, but it's a neutral molecule. B doesn't have enough electrons and it's positive, but C has a full octet and it's still negatively charged. So you can have a molecule that reaches the octet rule and is neutral, that reaches the octet rule and is negative. You see that with carbon and oxygen a lot. And there are molecules that don't reach the octet rule that are not positive. So boron, for example, if it has 3 things bonded to it, boron has 3 valence electrons to start with, minus 3 bonds. So this is a neutral molecule, but it's missing a lone pair. It doesn't have a full octet, right? There's a space for a lone pair right here. So technically, the octet rule and the formal charge may be related on some level, but for the most part, no. Don't assume just because there is or isn't a charge, it has a full valence shell or not. Okay, using curved arrows. So my description of what curved arrows serve is to show the movement of electrons. You make and break bonds, and you use them going from the area of electron density to where they're going to go to make the line. But I hope you can do that in your own words to show that you really understand the concept. So draw the appropriate curved arrows that result in the following product. So what I like to do in this case is ask myself, what electrons have moved? So here we have this is a ketone. Hopefully you remember that functional group. And there's an extra bond here that could move. So we'll see. But what happens is this bond goes away. And instead of having 2 lone pairs, you have 3. So what that tells me is this bond goes away and becomes a lone pair because you lose an electron here or electron pair here and you gain one up top. That's negative here, but it should also be positive down on the bottom because of formal charge. So this oxygen started with 6 minus 6 lone pairs, or 6 bonds minus, 6 electrons, sorry. Minus 1 bond is negative 1. And this carbon, it doesn't have any implied hydrogens. There, in this point, you have 1, 2, 3, 4 bonds to carbon. So there's no implied hydrogens. So this carbon started with 4, minus 3 bonds, and that equals plus 1. So that's positive. Okay, so in the next one, let's see, there was a lone pair here, and it looks like it turns into a bond, and it's bonding with this hydrogen. So this lone pair is going to leave the nitrogen, or sort of, and become a bond with that hydrogen to make this structure. So I like to think of it as like this lone pair shifts into being a bond to the hydrogen, but we draw that as a straight line instead of 2 dots. Now the next one is a little bit more complicated. It's through 2 molecules reacting together. Well, I guess this one was 2. It's a little bit more complicated though, and because there's 2 arrows. So, but it's the same concept. We look where electrons are going, and we just follow the arrows. They are going to tell us exactly where the electrons are going. So in this case, it tells you that these 2 electrons become a bond right there. And then this bond breaks and you add this here. So I kind of drew the extra line just to give you an idea of what to expect, but I'm going to draw the proper arrows back again. So this lone pair comes here to form a bond. Oh, I have too many there. And then this bond breaks and goes up. So I'll start with the bond that breaks and goes up because we've drawn that a few times, right? I made this oxygen negatively charged because now it has 6 electrons around it. Okay, so that was this breaking, but a new bond also formed, right? A bond formed between this oxygen right here, this lone pair became a bond to there. So this right here is what used to be this lone pair. I can even draw it in green for you. This lone pair turned into this bond right here. But nothing else, no other electrons or bonds broke, so we still have two electron pairs around this oxygen, and it has 2 carbons bonded off of it. So we have shown this electron pair forming a bond, but if it only formed that bond, this is something I kind of want to point out to you. If it only formed that bond and we didn't have the breaking of the bond ahead, can you tell me what's wrong with that structure? Why did the other bond break? Hopefully you notice that this carbon has 1, 2, 3, 4, 5 bonds, and that breaks the octet rule. So that doesn't work. So instead, this bond has to break and go up and become a lone pair with the oxygens. Okay. Is this the last question? Oh, not quite. Okay, so this question is about curved arrows to show the movement of electrons. So it's saying draw all resonance structures for the following molecules. What I do with resonance structures, there's a few rules. No atoms ever move, right? No atoms move. And you don't break single bonds. And you have to have a legit Lewis structure. So basically, you can't have too many bonds. You can't have an overly full octet. So these are kind of the things to check to make sure that you're not doing something wrong. But then you have to say, okay, well, I know all that's true. If we're not breaking single bonds and we're not moving atoms, there's only 2 things that really ever get moved around in Lewis structures or in resonance structures, and that's double bonds and lone pairs. And sometimes double bonds and lone pairs will be used to fill in a positive charge, and sometimes they won't. Bonds will just be made or broken or whatever. So that's where I start. I start to look for double bonds and I start to look for lone pairs and see if I can move them in a way that doesn't violate any of these other rules. So for this one, we've actually seen this same kind of thing a few times where we could break this bond and come up here. And so that resonance structure looks like O minus. So I have the curved arrow going from the bond that's breaking up to where the Lewis or the lone pair will go. So there are now 1, 2, 3, 4, 5, 6 electrons and 1 bond. So 6 minus 1, formal charge of -1. And then down here, this carbon is 4 minus 3, and there's no implied hydrogens because they would have been shown here, or we would have had to fill one in here. But it has 4 bonds, so 2 carbons and 2 oxygen bonds. So no implied hydrogens, so that equals +1, so this side is positive. So in reality, this structure, these are kind of your resonance structures, but in reality, you have something that looks more where there's like a partial negative, that little delta is a partial negative and a partial positive. And this partial positive center is very reactive. Things like to attack right there at that partial positive center. And that's all the resonance structures there are. But let's just check and make sure this one's good. Did any atoms move? No. We still have the backbone in order, carbon, carbon, carbon with an oxygen on top. Did we break any single bonds? No. We have a sigma, sigma, sigma. Those are all fine. I guess sigma bond is a better way to say that than single. are there any Lewis structures that exceed the octet rule? Well, nope. There's 2, 4, 6, 8 around the oxygen and 2, 4, 6 around the carbon. So it's not a full octet, but it doesn't exceed the octet rule. So this does exist, but it's less stable. And when something's less stable, it's also less of a contributor. So, if you're doing the average, instead of this being 50-50, this is more like 80-20 or 90-10% of the average. Okay, I think actually that this carbon dioxide one is really difficult. So I'm just going to show you what I would do. I would check this double bond and see if it can go here, because that's basically exactly what we did up there. And what that gives us is a very similar structure to what we did up here. So there's 1, 2, 3, 4, 5, 6 electrons in one bond. So that's negatively charged. This carbon lost a bond, so it has only 1, 2, 3 things around it. So that's positively charged. So this isn't super stable, but it does exist. Another option is to go here. Where this is 2 plus and both of these are minus. That is very unstable, and that is unlikely to be a major resonance contributor. This is the least likely to exist, so it would be a very small percentage of contributors. Now, another option, and I'm going to use a different color to draw this, is to break the bond and go to the other side. So if we have this structure, these two might look very similar. However, there's 2 different oxygen atoms, so we have to have a way to show that the negative charge is actually spread between both of the oxygen atoms. So the hybrid of these, or the average of these, would actually be something like this being like halfway negative, this being halfway negative, this being a little bit positive, and a slight double bond shared between the two. So we do have to draw both of those. And then there is a structure as well. This one's kind of, I would say this one comes up less often, but where you can fill in this and have the carbon full and the oxygen with a positive, but the negative charge wants to be on the more electronegative atom, so this isn't really a great structure. So these are the 3 main ones. I wouldn't count off for this, but it is not a main resonance structure. And then I'm going to check. Did any of my atoms move? No. And all of them, the carbons were in the middle and the oxygens were on the outside. Did we break any sigma bonds? No. There was always at least one bond all the way across. And then are all these legit Lewis structures? Do any have an overly full octet? No. None of these have more than 8 atoms around them. This carbon is 246, 246, and 2468. Great. And then these oxygens, 2468, 2468, 2468, 2468, 2468, 2468. So all those are good. Okay, so now we get to the last one, and I think what's difficult about this is what a positive charge indicates. This is sp2 hybridized, right? There has to be 2 hydrogens to get us to the formal charge of positive. 4 valence electrons minus 3 equals plus 1. So there's basically an empty p orbital here. And that means that this double bond, the 2 electrons in this double bond, can move and fill that in. So then you'd have your double bond over here. This double bond didn't move. And now these 2 hydrogens, they're implied, so you don't have to draw them in, but I'm just drawing it in so you can visualize it. This carbon now have 4 bonds to it. 4 minus 1, 2, 3, 4. So this is now neutral formal charge. However, this hydrogen right here, it lost a bond. So something's probably going on with it. Originally, it only had 1 implied hydrogen. So we're going to bring that implied hydrogen down. And So there's 4 valence electrons minus 3 bonds equals 1. So this is plus 1. Nothing else changed on any of the other carbons. So what this tells me is this positive charge isn't focused just on the end, but it's distributed throughout the ring, or throughout the chain. And then we can do that same thing again, where the positive charge is here. These lone pairs, they're the 2 electrons that make up that bond filled in over here. And now this has a positive formal charge. So in this case, what you kind of know from I'll draw all 3 of them out so you can see how to properly do this. There's a positive charge here, there's a positive charge here, and then there's... So the hybrid of all these are all pretty close to the same stability. This is a little bit more stable. We'll get into that into a later chapter, but pretty close. So the hybrid of all these has a partial positive on each of the carbons where the positive was shared. And then the double bonds, this double bond was here and here. This double bond in the middle was here and here. So those 2 double bonds are kind of spread among the whole thing. So this would be the type of answer I'd be looking for in a quiz or a test, with the double-headed arrows in between and in brackets to show that they're all hybridized. You don't need to bother about drawing this. I just like to show you kind of what the hybrid orbital really means, or what the resonance structures really mean. And then last but not least, oh, it's not last. Wow, I'm going to lose my voice by the end of this summer 5 weeks 1. Okay, so label each molecule as cis-trans isomers. My trick for cis-trans isomers is I cover up and look to see if 2 of the same atoms on the same side. So, no, I couldn't see any that were on the same side, so I'll get the hydrogens. In this case, these 2 hydrogens are on the same side. So this is cis because the same atoms on the same side. So this must be trans. So that's what I'll do, is I just try to cover up to get the hydrogens isolated. This is a single bond, so it can't be cis-trans. Let's count the carbons to see if it's a constitutional isomer. They both have 6 atoms. These are identical molecules because single bonds can rotate. So if this rotated, it would be the same as this. So these are actually the same molecules. It's not cis or trans because it's the same molecule. This one has a double bond, so it looks like it could be cis or trans to me. Let's see. So this looks like it's trans because if you cover up the double bond, there's a hydrogen and a CH3. And if you cover up this double bond, there's an implied hydrogen here and here. So, and everything else on the molecule is the same. So these are cis-trans isomers. And then this is, let's see, 6 carbons, 2, I just did the thing I don't like to do. 2 hydrogens here and here, here and here. So that's 12 hydrogens. C6H12 is the total here. This is 1, 2, 3, 4, 5, 6 carbons. And then there's 3 hydrogens here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So these are different molecules. These are not isomers. They have to have the same number of carbons and hydrogens. And I could just tell visually that these all do, right? This has carbon, 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 2 hydrogens, fluorine and chlorine. This we counted up to make sure they had the same number of carbons and hydrogens. This one, cis and trans, but we made sure that they have the same things attached. And then these are different molecules. Okay. This is making your own isomer. So 2 compounds with the formula C4H10. So I'm going to let you in on a little secret. If it's a plain chain like this, the number of carbons times 2 plus 2 is the number of hydrogen atoms you're going to have. So This is 5. 1, 2, 3, 4, 5. So there'd be 3 hydrogen atoms here on the outside. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 5 times 2 equals 10, plus 2 equals 12. So when I see this C4H10, I'm thinking 1, 2, 3, 4 carbons, and then 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So this is C4H10. Now, a good way to make an isomer is to branch something. So I'm going to take this methyl group that was attached at the end and put it in the middle. And then I'm going to count up. I still have 1, 2, 3, 4 carbons. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens, plus 1 hydrogen right here. Okay, so 10. So here are 2 compounds with that formula. Oh, this one's harder. C3H8O2. So C3, 1, 2, 3 carbons. So H8, 1, 2, 3, 4, 5, 6, 7, 8. But I can't do that. So I think I might do OH right here to do an alcohol. So that's carbon, carbon, carbon. I have one of my alcohols that I need. Could I do a second alcohol? 1, 2, 3 carbons, 2 alcohols, or 2 oxygens, and then we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Nailed it. So that's one compound with that. I think a very similar one is I can just move one of my alcohols. So 1, 2, 3 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 2 oxygens. Yep. So that's right. I'm supposed to do 3 compounds with this. Maybe we could do this. So I kept the 3 carbon backbone in all of these and just moved the alcohols around. So let's see. This is 1, 2, 3 carbons, 2 oxygens, and then 1, 2, 3 hydrogens, 4, 5, 6 hydrogens, 7, 8 hydrogens. Nailed it. So these are all constitutional isomers. This and this is constitutional isomers, whereas these are cis-trans, which are stereoisomers. And we'll talk a lot about stereoisomers. So these have the same, well, not all these are cis-trans, but like these would have the same condensed formula. This would be CHF, CHCl for both of these, right? Cis or trans. So you'd have to say which one it is with the cis or trans before it. These would be totally different condensed formulas. It'd be CH3, CH2, CH2, CH3 for this one, CH3, CH with a CH3 in parentheses to show that it's branched off that chain, and then CH3. So totally different constitutional or condensed formulas means condensed isomer. Totally different condensed formulas means constitutional isomers. Okay. The last one is which molecules are capable of cis-trans isomerism. So for cis-trans, you need at least 2 of the same molecule. So that can be hydrogen or that can be anything else. And they need to be attached on carbon. I'm just going to number these 1 and 2. You need to have 1 on carbon 1 and 1 on carbon 2. If they're on the same side, you can't do cis or trans because it doesn't matter. There's no rotation to flip that bond, right? So this would not be capable of cis-trans isomerism. You need 2 of the same, at least 2 of the same molecules, 2 different molecules. I don't know where my brain is going. My Adderall's wearing off. 2 of the same hydrogens. I have ADHD. It's prescribed Adderall. 2 of the same hydrogens, and then 2 other molecules, usually the same, to actually be capable of cis-trans isomerism. So this carbon-carbon right here, carbon-carbon bond, it has 2 hydrogens over here and 2 bromines over here. This is not capable of cis-trans isomerism because if you swapped these 2 out, you would get the same exact thing. So if you like broke this bond and moved this over, like I showed in class, it would be the same. So that's not capable of cis-trans isomerism. B is, let's see, that's also not capable of cis-trans isomerism. If you cover this up, yes, there's two of the same things on one side, but then you have to have two of the same type of molecule on the other side, or same type of atom on the other side. And there's not. There's bromine and hydrogen. So that, again, is not capable of cis-trans isomerism. And part of that is like if you broke this bond and moved the bromine up here and put the hydrogen down here, this bromine's still across from the hydrogen. So these molecules are the same. You could just flip it over and get the same thing. So they're not different. They're the same molecule. So that's not capable either. The other thing is you can look at the condensed formula. So this is CH2 CBr2. And it doesn't matter how you flip it, it doesn't change what the molecule is. And then same thing here, CH2, CHBr. So these are the same molecule. You don't need to write cis or trans because either way you attach this bromine, it's the same molecule. So there's not like, that should be Br2. There's not any confusion about where you put the molecules when you go, or the atoms, when you go from condensed formula to the dash structure, because there's no cis-trans isomers. No matter what you do, they're the same molecule, if that makes sense. Now, this has all the features we need. I can already tell because it has a carbon with a bromine and a bromine. Nope. It has a bromine and a hydrogen on one side, a hydrogen and a bromine on the other. So if I break this and flip it, we'll get a bromine and a bromine and a hydrogen and a hydrogen. So see how, like, when you flip these, nothing changes. When you flip these out, the thing on the other side is like still both hydrogens. So if I cover it up, you always get an H and a Br on this side of the double bond, no matter how you change it. This one, you get an H and a Br on one side of the double bond and two bromines or two hydrogens on the other side of the double bond. So breaking the bond and swapping it out on one carbon or the other does make a change. So this is cis, and this is trans because they're opposite. Now the problem we have with this D is basically it's the same as B, but just inverted. It has too many bromines, so there's not only two of the same thing, and then this has only bromine, so that can't do anything. So only C works on this one. If you want to do a little extra to challenge yourself, I forgot to tell you, you should be able to assign primary, secondary, or tertiary to each of these functional groups here. And this is an alcohol, so this is this is a secondary alcohol. This is a primary alcohol, primary, and this is a carbon, but it's attached to two other carbons. So even though there's three bonds coming after the carbon, that's secondary, not tertiary. Okay, well, I hope that was helpful to you. If you have any questions, please feel free to reach out and let me know. And I hope your studying goes well.